All right. Hey, everybody. We are just about to be at the hour mark. So we're going to wait just one, maybe 2 more minutes as people start filling in, because people are now starting to jump in. So, give us another minute or two. We're just going to give a little bit of time for everyone that can jump in to jump in. And let me think if there's any house cleaning. So, to go over the agenda really quick, I'm just going to give a super fast overview over the ecosystem for anyone who might not necessarily be familiar with it. This will be a lot faster than the previous webinar. So if you've been here before, we're going to do that a little bit faster. Then I'm just going to hand the reins off to Tom, and Tom's going to walk us through the workflow that he built for running NLP and starting to featurize and data clean up a bunch of text data for further analysis. He'll then take that same demo and scale it up to a multi-GPU environment in case you have too much data to process on one GPU. And then we'll have a Q&A. So I'm just going to give it one more minute. Another house cleaning topic is, while Tom is going through the first part of the demo, you will be able to fully follow along on that demo. So to do that, you'll need a user inside app.blazingsql.com. If you've never logged in, it just needs a G Suite login, and then you're in, and you'll have a whole Jupyter Notebook environment, and there's going to be a welcome to Blazing SQL Notebooks repository with everything that you need to get started. If you're a returning user, you're going to have to update that directory and that repository, and Tom will walk us all through that. So you have the latest and greatest. And with that, I think that we're basically at the point where we can get started. Just give me a little bit, because I want to share the YouTube link with the world, and then we can get going. All right. So let's get started. So for this talk, we're basically going to be going over an NLP, a natural language processing analysis, on a bunch of scientific journal papers with respect to COVID-19. So super timely topic, really, really interesting stuff. But before that, we want to talk a little bit about the ecosystem. So for anyone who's not familiar, we're Blazing SQL. We've built a GPU accelerated SQL engine, which allows you to run incredibly high performance queries let's just jump to it, on data frames, right? So Blazing SQL is effectively a SQL on data frame engine. And this is just a really simple example I always show off, where if you're familiar with pandas, cuDF is effectively pandas data frames, but on GPU memory. And you can read in a CSV. You can create a table off of that using this statement. And now because cuDF is able to, parse out the header row if it exists and infer the data types, we can now run full ANSI SQL compliant on these data frames. And this is all part of a greater open source ecosystem. So if you're not familiar with Rapids, I really heavily suggest you check it out. If you're using Blazing SQL is the SQL engine of the Rapids ecosystem, which is dedicated to doing end-to-end data science on GPUs. And there's not just cuDF, which is the data frame manipulation, but there are more and more libraries for machine learning, deep learning, visualization, so on and so forth. And Dask is really the thing that brings it all together for a multi-node distributed environment. So if I'm trying to run SQL queries on multiple GPUs or cuDF data frame manipulations on multiple GPUs, I'm going to need to use Dask. If I want to do machine learning on a distributed data frame, that I'm going to need to be using Dask. And so we'll go over a little bit of that during the demo. And real fast, just to kind of show off what the Rapids ecosystem kind of looks like. This is not an exhaustive list of all the packages. There are a lot more packages now that belong to the Rapids ecosystem. But on the left-hand side, you can see kind of your ETL, data manipulation, data transformation packages, such as Blazing SQL with SQL, cuDF and cuIO for the data frame, and then cuML for machine learning, which literally mirrors the same API as scikit-learn. cuDF mirrors pandas, cuML mirrors scikit-learn, cuGraph mirrors NetworkX, and so on and so forth. for you to be able to do all sorts of analysis. So with that all said, I really wanted to dedicate most of the time to the actual demo because there's a lot of rich content in the demo. So Tom, if you can unmute yourself and get your video going, I'll stop sharing my screen and you can go.
Sounds good. Thanks, Rodrigo. Can you hear me?
Yep, good to go.
All righty, let me share my screen. And let's see if this is gonna work. Okay. All right. Well, so welcome everyone. I'm glad that you are joining us today. And I hope that what we're going to present to you today is going to be quite informative. So as Rodrigo said, you can navigate right now to app.blazingsequel.com and then just simply use your Google credentials to sign in into the app. It will automatically provision a new workspace for yourself. And then if you navigate to Welcome to Blazing SQL Notebooks, you should be seeing webinars folder over there. That's what we're going to be, using today. Now, if you do not see this, I would suggest you go to launch a terminal and try to navigate inside the welcome folder. So here we are, and then just do git pull origin master. It should be, mine is already up to date, but if yours doesn't, then it should update right now. And then most likely you might have to do a git checkout master in order to switch to the master branch. So this way, you should see the webinars. If you still cannot see, or if the repo didn't update, ping Rodrigo and he'll walk you through how to get up to speed with this. But I hope you guys can see the webinar. So inside the webinars, 2 weeks ago we spoke about the Seattle parking example that we have over there. So that code is already available to you if you want to go back through that piece of code. And also we will share with you the recording from that session. Today, however, we will jump into the COVID example. So there's a couple of things here where we're going to explore today. The first one is the data exploration. To give you a little bit of a background, back in, I believe that was in May, Allen Institute for AI, which we call it here AI2, and a bunch of other partners that they partnered with, along with the White House, they actually curated a corpus of the scientific literature on coronaviruses. It's not only COVID-19, but it's pretty much all the past literature on coronaviruses in general. And they published that as a part of the Kaggle competition. I personally didn't take part in the Kaggle competition itself. However, I downloaded the data and started thinking about how we can use this data set, how we can curate this data set to create a model that ultimately will allow you to ask questions against such model in a line of, okay, what is the spread rate of coronaviruses in Japan? And the model should take that query from you and return a list of papers that are most likely containing some information about spread rate of coronavirus in Japan. So that's the ultimate goal. Today, we will walk through two steps of that ultimate process. So we will explore the data first and clean it up. I always say that any data set that you are given is guilty until proven innocent. So this the opposite. It's definitely, there's some issues with it. So it's our job as data scientists, as machine learning engineers and scientists, to first get familiar with the data, but also clean it up, right? There's lots of issues with all the data sets. Today we're going to be talking about finding duplicates, finding missing observations and stuff like that. and also getting familiar with the data itself, right? It's really, in the age of deep learning, people might think, okay, well, I don't really need to care about that much about cleaning the data, because the deep learning model is somewhat implicitly going to do that for me. It's not necessarily always the case. So I prefer to start to be more familiar with the data that I deal with, rather than rely on a model to kind of handle that gracefully. So that's going to be the first step. And then the second step, we will look at the at the data set from a slightly different angle. Ultimately, what we want to do in this whole process is to build train a BERT model. Train a BERT model in a way to recognize the missing, obscure tokens. So predict the next word in a sentence. But the ultimate goal is to actually extract the embedding layer from the trained BERT model, and based on that embedding layer, train another model that does unsupervised segmentation of papers. Therefore, later on, when we say, okay, well, what is the spread rate in Japan? We can use the embedding layer from trained BERT model and return a cluster of papers that are most likely the closest to the question that you've asked. So in the second notebook we will walk through today, we'll process the text, the actual raw text of every single paper that we have in the data set, and featurize it in a way that we will use a GPU-accelerated tokenizer in order to prepare this corpus for training BERT model. So I'm assuming right now that you guys can see the first notebook, the data exploration, so we can actually start moving on with this. We will be using cuDF in this example, because the data set is not as big as, that it wouldn't fit in a single GPU T4 that you guys have access to right now. We'll also use a little bit of pandas every here and there. So that showcases how easy it is to cooperate between pandas and cuDF. We will use JSON and S3FS because all the data that we we downloaded, we actually uploaded to our S3 bucket for easier access for you, for all of you. So let's import all the necessary modules we're going to use today. And then first of all, we will retrieve the data. So the data lives in this BSQL data COVID bucket. And from over there, there's one data set called metadata.csv that has a full list of all the papers purportedly available in this corpus. So if you run this, it'll actually show you ahead of that data set. It might take a little while, because right now we are moving that data set over the wire, and that's roughly 400 megabytes, but it shouldn't take too long. And you can see that we have some IDs, the hash of the actual data set, source where it was sourced from, the title of the data set, DOI, and a bunch of other descriptive information about the the papers themselves. Plus, it actually contains the URL where the data the paper was downloaded from. One thing that we will be heavily relying on is this PDF JSON files. This is a link to where this particular raw data for this particular article, for this particular paper is available. As before, cuDF has the list, can return the list of all the columns. So this is the list of all the columns we have. However, we will be mostly focusing on this subset. So title, abstract, and authors, published time, source. So this is the source where the article was originated from, where it was published, so the journal, and as I said, the PDF JSON files, which is a link, a physical in quotation marks, physical link to the file where that paper can be linked to.
Hey, Tom.
Yes.
1 second. We're just trying to get some people up to speed with with the actual notebook. So real fast, if you've been following inside the chat and you don't know where the notebooks are, Tom, can you show them the path to those notebooks real fast in the left-hand menu there?
Okay, so we start effectively, you should be seeing, forget about the webinar, you should be seeing when you log into the app, you should see the Welcome to Blazing SQL folder. And inside there, there's a webinars folder. So if you don't see webinars, we need to get you up to speed with this. So raise your hand if you don't see the webinars. But inside the webinars, we are...
Christian doesn't, Rashmi doesn't. So okay. Christian and Rashmi, what we recommend doing, one, if you don't have the Welcome to Blazing SQL Notebooks directory at all, that is certainly not what we would have expected.
Yes.
You should definitely have it. If you do have it, hold on a second, but if you do have it, but you don't have access to the actual webinars notebook, then just git clone the repo I sent in the chat, and you can see the link for the .git, and you can do that inside your terminal. So what you have to do is you just have to run that git clone inside terminal. You would do it from your root directory. You don't need to do it anywhere else, and then it should clone it in there. For anyone else, yeah, you'll have to do rmrf. You'll have to force it. That was my bad for not sending that. You'll just want to rm remove that whole directory, Welcome to Blazing SQL Notebooks, and re-git clone it, and you should have it. So we'll give everyone just, a little bit while Tom can jump back into the notebook itself.
Okay.
If you still have issues, just send me a direct message and I'll try to see how I can help you out. But in the worst case scenario, I can help you out after this and make sure you have everything you need. So Tom, I think that's as much time as we probably can wait around. So why don't you just pick it back up?
Sounds good. All right. So just like before in the previous, in the previous webinar, we will be using Blazing SQL as well to help us to manipulate this data. Certain operations that we will be doing, for me, easier to express myself in SQL language. So we'll right now instantiate the Blazing context and create the metadata table. So right now, this bc.create table metadata, that's going to be the table, the name of the table that we will be using. And as you can see, I'm pointing that to the cuDF data frame metadata. So ultimately, Blazing SQL creates this abstraction on top of the cuDF, the data that already sits in memory, and we can use SQL to manipulate that data. So first of all, I normally like to start by seeing, okay, well, how much rows do I have in my table? So in this particular case, we have 233,000 articles, and that's quite a bit. So when I first downloaded this corpus from Kaggle, I believe at that point in time, which was roughly around May, there was around 110,000 articles already in that corpus. And this corpus, we provide this the link to that particular, if you want to look at the historical releases of this corpus, it changes pretty much every day. So there's a bunch of scientists that if they see a new article coming up on COVID or coronavirus, they pretty much add it to that repo and then release as a new release. In this particular webinar, we are using the corpus as of August 24th, but I believe there's more right now that you can download from. I need to update that link actually. Anyway, so we have 230,000 articles in this particular corpus. So let's look at the source. Let's look at where this data was published. So most of these papers were published in the WHO website. So this is not really that surprising. WHO was really heavily bombarded this year, especially with releasing all the press releases and everything that's related to coronaviruses. So I'm not surprised to see 65,000 links or 65,000 records linking to WHO. And same with Medline. These all definitely gives you a sense of where the data comes from. And then same thing, I like to understand where is this, what journals actually, publish these papers. So bioRxiv, BMJ, Journal of Virology, definitely that's something that you would expect there. Nature. So all of these make sense, right? So for me, this is a sense check. This is a sense check in a way that, okay, if I see a journal of air transport management here, it means that something is not really right, unless it's a paper on journal, on the transportation in the era of COVID, and then probably that's something that I would check out. But if I see something at this stage, something that's eyebrow raising, then I would probably start looking into that subset of articles in a little bit more detail in order to further understand, is this article really should be here, or should I remove it from from further investigation? Now, when I first run, when I would like to look over the years how that, the data publishing changed and how many papers were published over the years, you can see that, around 2003, you start to see a big spike. So it was trending around, I would say, probably up to 500,000 papers a year over the years. But suddenly in 2003 and 2004, it jumped, pretty much 6 times over the baseline from the previous years. And that's pretty much the time where, SARS hit in Asia. So Asia was, around that time, there was a big, it's not pandemic, it's kind of like a more, localized, what's the word for that? I can't remember now. But localized, spread of coronavirus in Asia that effectively quickly was contained and eradicated. But you can see how much papers started being published after that period of time. So it kind of quickly ramped up to 7,000 papers a year, starting in 2014, 15, 16, and so on. Now, you might notice that I removed 2020. And I did that on purpose because when I first ran this particular query, this is what I see. You can see the stark difference between how many papers or how many mentions in the metadata file were there in the year 2020. We also already have something for 2021, which is a surprising development there. But you can see that 2020 dwarfs all the previous years. As I said before, like from this chart, you can see it kind of plateaued around 7,000 mentions, 7,000 papers a year in 2020, and we still, it's only end of October. It's already at 140,000 mentions of coronavirus, which is not surprising. Of course, it all started at the beginning of the year, and everybody jumps in order to help out, to analyze, to provide some guidance, and and everybody talks about it. So I'm not surprised by that. But that chart here, it literally tells me we are in a serious predicament right now. Even without that chart, we know that. So that gives me some feeling that, okay, well, what I'm seeing in this data set kind of makes sense. So right now, this is pretty much the time where I start to move to data cleanup stage, right? So when I look for missing values, when I look for duplicates, when I look for, okay, do I have all the files in this, all the JSON files that are listed in the metadata, data frame, can I find them on the disk? So I'm starting with missing values. So what I do here is I'm looking only at the subset of columns from, so I'm literally trimming most of the the ID columns and most and a couple of the other links to the other files. But what we do here is that for every single column, this case statement here, this is a SQL expression to say, okay, well, if this particular column has a null value, just give me 1, otherwise give me 0, and then create a new column that's called that particular name of the column _ miss. So this is pretty much what this particular query would do. And what this query does, it effectively goes back to this missing flags query that we will create here, and scans through every single column once more time, selecting the missing column and creating the missing flag for it. But also at the same time, it gives me a flag, counts how many missing observations I had over there, but also gives me a total count of rows that I have in that particular data set. And then ultimately, what we are really interested about is, okay, well, what is the percentage of missing observations in that particular column? So if you run this, that shouldn't take too long. We have 100% miss. So this mag_ID column has missed, like it's literally, there's nothing that would be of interest. Archive ID is missing pretty much all of it. So only 2%, well, actually 1.5% is non-missing. WHO confidence ID missing 28%, and so on and so forth. What is more problematic is that we see this particular, the PDF JSON files, this is a link to a physical file in the folder that we would like to extract. And if this is missing, it's a kind of useless information, information for us. And that's almost 60% of the cells in this particular column are missing. So that's more worrying, and then we'll look into how to do that. The query missing, this is literally giving you what the query would looks like, and same for the when we create this aggregated view of how many missing observations we had in each column. So what we can do right now, so we are missing 60% of values in the PDF JSON. So what this query does, it tells, it instructs, Blazing SQL. So just give me all the observations where the PDF JSON file is not null. If we don't have a link, we cannot do much about it. We cannot, map this particular, article to a physical location, physical file, JSON file, and we cannot read it because, and we won't be able to read the raw text of the paper itself or the node itself. So there's no point of having that, in our data set. And that quickly trims the length of that data set from 230,000 to 94. So it's okay. It's okay. We can double check right now. So see the missing percentage points. We still see 40% missing for the WHO confidence and MAG and archive. This is okay because most likely, if the paper is published on the WHO side, it's going to have the ID from that website, versus if it's published on archive, it's going to have the ID from the archive source, but WHO confidence will be missing for that. So that makes sense. The rest, title miss, that's probably a little bit more worrying, but it's only one article, so I think we can neglect that. So now let's look at the duplicates. The duplicates can be, the true duplicates, as I say. The true duplicate is effectively a almost exact record appearing multiple times in the corpus. This fake duplicate, as I like to call it. The fake duplicate is, it has the same ID, it has the same, it points to the same file, but the metadata about the paper itself are different. So it might have different authors, it might have different title. It's just that coincidentally somebody put, the same, ID and the same link to the file, by mistake. So this is the code here that helps us to figure out, okay, how many duplicated information we have in our data. So the URLs, we don't see any duplicates, which is good. Title has 1,200, so we need to look into that. these are exact duplicates, right? So what happens here is we looking into, exactly, do I have an exact, count that matches exactly the same title. This is an exact match. The way we do this is we are counting how many articles do I have in that particular column, and also counting distinct. So you can see, where do I see select pattern here? So we're doing the select pattern is the distinct. We've calculated that earlier. So it literally calculates just the difference between, okay, I have 100 articles there, but the number of distinct articles in that particular column is, 99. It means that I have one duplicate over there. So we have 1,200 duplicates in titles, 300 in abstract, and 6 in the PDF JSON files. So I'm going to start with the PDF JSON files and just bring up all of those that have a count of articles or count of the PDF JSON files greater than 1, right? So this is a list of 5. It tells me that, okay, we have indicated that there's 6 duplicates. It tells me that since we've retrieved only 5 records, one of these is triplicated, right? So it has 3 rows, 3 exact PDF JSON files, 3 exact same values. So let's pull them up. So this query here effectively uses this join, this query to select PDF JSON files that are that have count more than 1, and that inner joins that with the metadata no missing, which is already the a little bit cleaned up version of our metadata table, to pull up all of these articles, all of those papers that we found that are duplicates. And you can see that this is exactly the same ID. It's exactly the same ID. And when you actually look at the title, they're different. So that's exactly what I was talking about. These titles are different, right? And they are published in slightly different places. This one is also in WHO. The abstract is missing, but it's different. And more, more onto that, the list of authors is different as well. So it tells me that this is really not a duplicate. It's somebody made a mistake and pointed that to the same file, JSON file. However, when you look further down, you can see that these are exact duplicates. They are published in different, sourced from different sources. But actually, when you look at the title, it's exactly the same. When you look at the list of authors, it's exactly the same. The publication date is different, right? But I think, and then even the diabetes, I'm not really familiar with this particular journal, but they look the same. So it tells me that I can drop one of them and then, and then just keep one because it's going to be the same file. However, since we only have like 6 duplicates, we won't play that much with this. So we're going to drop all of them and then just move on. So we are only, as you can see, this particular query here. Previously, we had, okay, just give me the files that have more than 1 occurrence in the dataset. Right now, keep only the rows that are exactly occur in the in the dataset only ones, based on the count of PDF JSON files, based on the count occurrences in this particular column. So now let's move to let's see the title duplicates. Title duplicates, we follow the similar pattern. So we extract all the rows from the metadata JSON clean table that has a title greater than 1, more than once, appearing more than once. So let's look at that. There we have it. So you can see that they do appear to be pretty much the same articles. The authors the authors seem to be the same. There might be some, abbreviations that are different, but they seem to be the same. Also published in the same journals. What is surprising is that the year published is different for most of them. But in this case, what we are going to do is use the drop duplicates from cuDF to just the subset switch here, the subset parameter. It instructs the drop duplicates to only look at the duplicates in the title column, and then only keep one of the articles. So randomly, I don't think we're gonna suffer from much. It's only 1,200 duplicates. We will keep only one occurrence of that duplicate. So finally, we don't check that we don't have any more missing duplicated titles in our data set. And final thing that I want to check is that, do I have in my in the folder with all the JSON files, do I have all the files that I have linked to in the metadata table, but also check, do I have more files in that folder that they do not exist? There's no link to them in the metadata table. Effectively, we are creating this Venn diagram. Here's the list of files that I physically have on disk. Here's the list of files that I have a link to in the metadata table. What is the intersection of these two sets? So when we look at this, this will take a little bit, because right now we effectively are going to the S3 buckets that we have over there, and then listing all the files that are in the document parsers PDF JSON. So that might take a second there, but it shouldn't be too long. Normally it doesn't take too much. Yeah, there you go. So here's a table. Here's a summary table, right? And then we can see that, okay, well, I have a meta PDF JSON link in the metadata table, but I cannot find the related JSON file on the disk. So there's 5,000 occurrences like that. On the other hand, we also have 12,500 files that are physically located in the folder, but I don't have any indication, any link from the metadata table related to those files. And ultimately, 87,000 I can find in both places. So that's my intersection. So in the end, we are going to keep only 87,500 articles that we have in the metadata table right now, and we will call it metadata PDF JSON clean. So that's 87,438 articles that we will look at later on today. And then ultimately, let's print it out. So the query select from everything from that table, save it to disk. So this way we are going to have a metadata clean should show up in the COVID folder. There you go. So now that we have looked and get a little bit more familiar with the metadata, let's look how we can process this data and featurize it for the usage in the, how we can prepare that for the BERT training. So once more, we will import everything that we need. We will import cuDF, pandas, and then S3FS, and so on and so forth. So first of all, we are going to read this metadata clean back. So that shouldn't take too long. And in this free version of the webinar, we will only look at the first 300 articles. The reason for that is the JSON files that were dropped as part of this corpus, they are in a really hard to read format. They are not, JSON files that are lines formatted. So each line is effectively a dictionary that can be quickly parsed by either pandas or cuDF or Dask cuDF. So we need to reverse to reading every single, like literally looping through all of these files, opening every single one of them, reading that with JSON, and then effectively creating a one row data frame by using these extracted keys from the JSON. So we will keep the hash of the article, the section title, the paragraph count, and the text of the raw text of the paragraph. So this, I'm going to start to run this because that takes roughly 30 seconds to run. But ultimately, what we are trying to do here is to read all of these information from from every single JSON file, and ultimately, once we've processed all of these, we end up with a articles list that contains every single element. There is a cuDF that we can finally concat here to create the full list of articles, and ultimately we ending up, so from 300 articles, we end up with roughly 12,000 paragraphs extracted from those JSON files. So first step on this journey to tokenize this text is we need to build a vocabulary. If you're familiar with BERT, BERT's vocabulary is effectively a Subword vocabulary where you have, if you have a word activate, for instance, right? It can be, it normally would be split, in the BERT vocabulary into act and wait subwords. So we need to create these, this particular representation of the vocabulary, but based on the corpus that we are working with. So what we are going to do here is to tokenize the articles first. We will use the string tokenizer from cuDF, lowercase every single word in that document, and also remove some of the unnecessary things that we don't really care about and replace them with a blank character. We will also add a counter so we can group by text and count how many that particular word occurs in the data. So if you run this, you can see that the total number of tokens is around 3,000. So from this 300 papers and roughly 12,000 paragraphs, we can condense this to a list of 3,000 words and count how many times they appear in the corpus. So we have the word "the" occurs 74,000 times, where the word "off," "on," and "in." This is just the head of that file. We also have this empty character, so we are going to use only. We're just going to remove that 0th row from the data. In order to create this representation that BERT would require, where we have the subwords in the vocabulary, we are going to use this text encoder. This is the text encoder that I borrowed from this repository. I provide you the link there. I slightly modified it. You can find it in the scripts, scripts folder. I'm not going to go into many details around how this is, these algorithms work here. You can see that BERT requires these additional special, keywords for padding, for end of sentence, for unknown if it cannot, decipher what it doesn't know that particular word, and so on and so forth. What effectively this script does, it iteratively tries to find the longest subtokens in each of each word and see how many times it occurs in the. If I had split all the other words on that subtoken. So if you look at this example here, I'm not sure if this is probably a little bit too small. Let me try to make it a tad bigger if I can. Doesn't look like I can. All right. If you look at this subtoken here, it can be this token here. It can be split into subtokens 1, 2, and 3, 4, and then from all of these combinations would be created, and these combinations would then be checked against all the other words, how many times they occur, and if they occur enough times, they will be kept as another subword that is added to the corpus. Otherwise, they will be dropped. So I'm not going to go to too much detail into this algorithm, but when you run this and you take this particular token counts cuDF and then convert it into a dictionary, where the key is the word and the value is the count of how many times that word occurred in the data set, we can quickly generate a vocabulary of going from 3,000 tokens, it will expand to 13,500 subword tokens that are ultimately going to go into our vocabulary table. So if you open this, you can actually start seeing how does that work. So as I said, like you can have, the word ability. The double hash in the, in the front means that it can be disability or unavailability or something else. So the bird will ultimately look for these, subwords and then try to make sense out of those. And that's effectively what we really need in order to use the subword tokenizer later on. And then the subword tokenizer requires actually taking this vocabulary, but in a hashed form. So good folks from the Rapids team that work on clicks created this perfect hash script that effectively, hashes a vocabulary of up to 65,000 words and creates a hashed representation of that is guaranteed not to have any collisions in it. And that particular file can then be used by the subword tokenizer. So we will use this particular script quickly to create the hashed vocabulary representation of our vocabulary. And now, right now, this is where the the subword tokenization currently we can use the subword tokenization. So the subword tokenizer effectively uses this vocabulary hash and the way that BERT requires the data to be formatted, and produces, effectively it produces a long CuPy array of 256 elements per per row in the original frame, and if the text is shorter than 256 words, it will pad it to 256. If it's longer, it will just truncate it there. So the do truncate set to true effectively sets that sets that. We will be specifying the number of strings to return to be equal to the length of the frame. And effectively what we get back is a data frame with two columns, the tokens and the attention. So when you run this is really quick, right? So I remember when I first, before subword tokenizer was introduced in Rapids, it took me, I think, an hour to literally run through the whole data set and tokenize the text. So the tokenized, what you can see over here is that, okay, for every single row in our original data frame, now we get encoded tokens. The attention column here tells the when you train the BERT, it feeds through and then tells the model which words to pay attention to and which words are simply padding in the in this particular vector. And of course, this is all done. So BERT requires, just like any any deep learning model or machine learning model, it requires a value representation, a numerical representation of the data that you deal with. It cannot deal with text. So that's why this is the very quick way of featurizing your data to produce this representation that BERT requires. And let's check how many tokens we ultimately have. We have 3 million tokens in this particular data set. So there's 3 million tokens. This particular data frame is 3 million rows long. Now, as I said, as we indicated here, every single row in this data set is, should be 256, values long. So if we take the tokens count and divide it by 256, it should equals to the number of articles, or actually the number of paragraphs that we had in the original data set that we read. So if you run this, it actually makes exactly that number. So if you take the total, the 3 million divided by 256, you end up with 11,807, and that's exactly the number of how many paragraphs we had in this corpus. Now I will show you, how to take it to the next level. Take it to the where you can. Let me just double check if my cluster is still up and running, because it might have shut down. Yeah, it has stopped. So let me start this again. I'm going to close this, go away.
So while we're waiting for that to stand up, does anyone have any questions that we could go over in the meantime?
This shouldn't take too long, but yeah.
Yeah, it'll take maybe a minute, so I'm just giving people the option. Yes, so the question is, have the Spacey and Hugging Face, yeah, I was assuming it was Spacey, yeah, Spacey and Hugging Face packages been optimized to work using Rapids AI? They have, in fact, been optimized to work with Rapids AI. There's a lot of information out there with how we use Spacey and Hugging Face on some, multi-terabyte benchmarks, actually, and more information will be coming out on that relatively soon. Do you want to add anything? Do you want to add anything, Tom?
So I totally agree with what you just said. Yes, Spacey has been optimized to use GPUs. In fact, there's two switches you can play with Spacey. You can either require a GPU or prefer GPU. That helps you to, if you alternate between systems, that are CPU only or those that have GPUs, the same script will run in both situations, but it will just select. It's going to be slower on the CPU, but it will not fail. If you require GPU, it will, it will fail if it cannot find a GPU. We didn't do it here, and for that, the reason for this is. I wanted to kind of focus more on how we use the cuDF ecosystem, and then the string functionality from cuDF specifically. But yes, that's a good point, and we had plans of including that later on. Does that help?
Cool. Let's get back into it.
Okay, so in this particular example, we will use all the files. So all this 87,000, all the 87,000 JSON files that we have. And I'm not going to run them right now. I've already run it, and then I uploaded this full text clean, Parquet file to S3. We will only use that, and we're going to just read that back in, and not just run it here, because it took 30 seconds to run. The only 300 articles. It will take us much longer to do that. The same here. Now I need to change the IP of the head node. Just bear with me for 1 second. And over here, we will.
You're going to want to use localhost now?
I can use the whole thing.
Okay. It just seems like it only is giving you one right now.
Oh, yeah, you're right. Okay, that's surprising. Okay, do this.
I don't think that'll work. You're going to want to use localhost now. Oh, there it goes. Never mind.
No,
I said
think
nothing.
if I do client restart again, there you go. Now we have 4.
There
Okay.
you go.
Yeah. So on the side, I don't know if you guys are familiar with this, but there's a really nice, Jupyter Lab extension that it allows you to track the progress of how you when you execute the cells with Dask. We are going to read Dask, the Parquet file. It's already partitioned into the articles table, so you can see actually. It returns immediately, but in the back, asynchronously, the Dask will currently read all of this data. And this dot persist, if you're familiar with Spark, the dot persist is effectively dot cache. It takes all of this data, executes the DAG up to this point, and persists that information in memory. So we will have that access to all of this in memory shortly. I've noticed that it stops a little bit. I think this is the S3 transfer that is getting blocked up over there. But ultimately, when this finishes, you will see that we have roughly, if my memory serves, I think, let's give it a little bit of a moment. It shouldn't take too long. I think it picks up again. Come on. Okay, so we'll have 2.9 million paragraphs in this articles data frame, and these occupy roughly 2.3 gigabytes in memory. Now, 2.3 gigabytes might seem like, okay, well, I can do this on a single T4 with 16 gigs of RAM and be done with it. The problem is with the Subword tokenizer as it is implemented right now, it requires much more memory in order to do the tokenization than it is in this data frame. So effectively, the documentation on Subword tokenizer tells that it requires 21 times the size of the data frame itself. That's why we will use that's why we're using Dask. Another reason is there's a limit of how long and how big the string column can be. And if you try to load the data into a in a single cuDF data frame, which is collect into in a single partition, it will also fail. This should be familiar. So the only difference between what we run in the free version versus this is instead of calling this tokenized frame as a function, we effectively map every single partition to run this tokenization, normalization, and replacing some of those unnecessary characters that we have in the text. So the map partitions, just to level set, for those people that are unfamiliar with how Dask works or Dask data frames work, Dask data frames are effectively collections of either pandas data frame or, in case of the Dask cuDF data frames. Right, so underneath the hood, every single partition is effectively a cuDF data frame. So the map partitions effectively takes and processes every single partition at a time, applying this particular, in this case, this particular function to it. So when you run this, you can see it starts executing, and that should be quite quick. The tokenization frames, as you can see, currently executing this tokenized frame. And we end up with 31,000 tokens. So that's the difference what we had. Before we had 3,000. Now that we're using the full corpus, we end up with the 31,000 tokens in our dataset. So you can see what this looks like. We have a counter. So this the head effectively this is the difference between Dask cuDF and cuDF. What it does, it goes to a single partition and then just returns the top rows from that partition. And I'm going to skip through this. We talked about the Subword tokenizer. Over here, we changed that a little bit. So right now we require that the frequency to to keep the word or subword in the vocabulary, the ultimate vocabulary, is 3000. And we will run 4 iterations in order to refine that representation. We end up with 13,000 ultimate tokens. So when you look at this, I'm going to run that. There you go. This is the vocabulary large. We end up with a very similar list, but it's much more, it kind of like, right now is able to handle all of these new words that showed up in this additional vocabulary. And in the same way, we are going to use this perfect hash to create this hashed representation of the vocabulary. Now, this is where the things get a little bit more complicated. So initially, when we try to run this with the vocabulary file, it will fail because that vocabulary file, this vocabulary hash large file, is effectively local to the submitter, to this particular client, this particular Jupyter Lab. So what we need to do first, this is a tiny file, right? So this is like 400 kilobytes. We can quickly upload that. So the upload file effectively takes this file from where I'm sitting right now, and it disperses that, loads that to every single worker. So right now, at this point in time, every single worker will have that file sitting in pretty much this location. I say pretty much because within that folder, there's a folder that matches this particular pattern. It's worker dash, and then there's a hashed ID of the worker. So every single worker, if you have a worker with multiple GPUs, there's going to be as many folders with worker dash as the number of GPUs you have in that particular worker. So we need to pull up that folder, and the vocabulary hash large will literally sit in that particular location. So if you execute this cell, notice that nothing happens because right now we only extended the graph of execution for Dask, but we didn't run an action on top of that. So when you actually run this, you can see we've chunked every single frame has been processed. Took 2 seconds to process the data frame that we had, and it generated 730 million tokens in this particular data set. And this is what it looks like. It looks the same way as we had before. There's tokens, there's the attention, and so on. And we can definitely check the same way, as we did before. Do we have the same number of paragraphs as we in the tokenized version versus the ones that we started with? So we went from 2.8 million to 730 million tokens in the data set, but if we divide by 256, we end up with exactly the same number of rows. Now, this representation we can right now take, reshape it to be a vector of 256 tokens long for both the tokens and the attention, and then start feeding that into the BERT trainer, which we will focus on in the next iteration. Now, the final thing that I wanted to mention here is that this final data frame, the tokenized data frame, consumes 5.4 gigabytes of memory. But as I said, this 5.4 gigabytes, even on a a single GPU with 24 gigabytes, it quickly runs out of memory because the Subword tokenizer requires much more memory than what you see here. And that brings us to the end. I definitely hope that you picked something that was useful for you, and then you've learned how to use the Subword tokenizer and also how to kind of get familiar with the Rapids ecosystem altogether. I think that's it. Off to you, Rodrigo.
Yeah, that was awesome. Here, you don't have to stop sharing your screen. Okay. If anyone didn't necessarily follow along at the end there, right? He just went from doing everything in the free app to then going to a multi-GPU cluster and scaling this up and running it on all 80,000 or 88,000 articles. There is one question from Michal, which is, would you have a link to read up on why the hashing is necessary and how it occurs? I'm not certain which part Michal might be referring to.
So I think the part is about the
perfect hash.
The perfect hash, the perfect hash representation of the vocabulary. Yes, and you can read upon that. We can definitely share the link. The clicks, team from Rapids, they literally talk about why this is necessary. The long story short, this is necessary because anything that you run on a GPU needs to be needs to be kind of like represented in a number. So it's much easier for the Subword tokenizer or the CPP C++ layer to handle hash tokens. So you have a number instead of a long string. That's one. And two, ultimately, what you feed the BERT model with is effectively a number. It needs to be a vector of numbers, right? So the hashing achieves that pretty much. It helps with two things. It helps with, one, speeding up the Subword tokenization, but it also, the outputs can be immediately used to train BERT. Now, just to add a little bit on top of how the hashing works, it's effectively a double hash, right? So you hash the first one, and you take that representation and hash it again in order to guarantee that if your vocabulary is under 65,000 words, it is guaranteed to be unique. So you can retrieve that token. There's no necessity to have a list in a place in a hash, as it is in the normal hash table.
Yep.
Yeah.
Yep. So real fast, we're obviously a few minutes over. So everyone who's stuck around for a few extra minutes, we super duper appreciate it. We're going to be doing these every 2 weeks. So in 2 weeks time, same exact time, we're going to have another one. We don't know exactly what the topic is. We have a few different topics that are lined up. We'll be sharing that in a couple of days to when we have the final decision. But there's extra versions of this particular talk coming out that take it now into BERT and how do you actually train BERT. So expect to see a lot of things coming out from our webinar series. And if you have any questions, you can always reach out to us, tom@blazingsequel.com, Rodrigo@blazingsequel.com. That's right. It's an incredibly fast tokenizer. Awesome stuff. And you can also reach us out on Twitter @blazingsequel. We're very active in Twitter. That's where we put everything new that's happening with the organization. And the open source ecosystem. So if you're at all interested, please let us know. And yeah, thanks a lot, Tom. That was great stuff. I love seeing these workloads.
Awesome.
Thanks, everyone, for joining. Thanks, everyone.
Take care.